Hi guys, Mrs. H here. Today we're going to be looking at the nature of matter and states of matter. So, in order to understand states of matter, we also need to understand the nature of matter. So, what is matter? Exactly what does that word mean? So, matter is anything that has mass and takes up space. All matter is made up of atoms, and those are those tiny little parts that we're going to look at later. And everything around us, whether we can see it with our eyes or whether or not we can fill it up with our lungs, so the visible and invisible things, these are all made up of atoms. So, atoms are those teeny tiny particles. We're going to explore what those teeny tiny particles are later. But all matter has atoms, they have mass, and they take up space. So, what does mass mean? Mass is how much matter there is in an object. So, how much stuff? So, if I'm packing all those tiny particles into that matter, how much of that is there in that substance? And the next thing is how much space or how much volume, how much length or width or height does that substance take up? So the space it fills and how much stuff is in that space that is filled. So that's the difference between mass and volume. And so matter has mass and it has volume, whether we can see it or not. So then we can look at states of matter. And so when we're talking about states of matter, we're looking at solids, liquids, and gases. There's actually a fourth one, plasma, and we'll take a look at that in a second. And when we're talking about those states of matter, we're actually talking about how much energy they have and that are associated. But each one of them have specific properties. And so the properties each one of them has will distinguish it from being a solid, liquid, and gas. So a solid has a fixed shape. So it has very definite shape. It has a very specific dimensions to it, regardless of where it's at. It does not have to have a container to have this. We also say that they're often crystals. They're very dense, but you can't squish it. You can't compress a solid. You also can't pour it, and it has a very definite or fixed volume. Now, liquids will take the shape of the container. So I can have water, and I can put the same water in several different cups, and the cups are what's giving the water the shape. They do not have crystals, but they still are dense, and they also can't be compressed or squished. You can pour them, like pouring them from one cup to the other. Now, when I pour it from one cup to another, the volume of that substance won't change. So I would always have the same volume. So, how much space is that liquid going to take up? That also will not change. Now, gases do take the shape of the container, but this is kind of tricky because a room is a container, right? And so we don't necessarily think of a room as a container, but it will take the shape of a container. I can also take all the gas in a room and I can compress it or squish it into a smaller volume, and so its volume will change. So I can take all the air in this room and I can put it into a canister, right? And so it's going to change in its volume because I can compress or I can squish it. And I can also change the shape of it based on its container. Now, it will not have crystals, and these are not very dense. You can pour them, and I know that's kind of weird to think about gas pouring them, but think of releasing a valve on a tank of gas, and what are you doing? You're pouring the gas into a new container. Some examples of solids, so Pepsi cans, books, ice, sand, buckets. Again, they all are having that fixed position, and all of the particles are locked or tightly packed together. Um, When we're thinking about liquids, we're thinking of oil or milk, and we can pour them into different containers. And what's happening to those molecules? Those molecules are actually slipping and sliding over each other when that happens. When water is emptied into a glass, again, it still has the same volume, whether I have it in glass one or glass two. But what's different between glass one and glass two is those two things have a different shape. And then examples of gases. So air that is in the atmosphere, the air that we're breathing, are gas. Oxygen is a gas. The helium in a balloon is a gas. So again, they have no fixed shape or volume. They're all going to have the shape of the container. And these particles, because they have so much energy, are going to spread out as far as they can. So let's go ahead and do a think about it, a comprehension check. Can you think of or name two solids, liquids, and gases in the following picture? So, how is the kinetic molecular theory related to the different states of matter? So, matter is made up again of those particles, but those particles are in constant random motion. And that motion is going to be defined or sorry, the amount of space and mass it takes up is going to define its state. But a second part of that is those states have different energies, and those different states have different motions of their molecules. And so that's really the defining characteristic. It's actually a more accurate definition of those states. So let's look at how the kinetic molecular theory applies to the states of matter. So remember, solids like sulfur and copper, these are substances that have their own shape. Liquids take the shapes of their containers, but gases are going to spread out, and their volumes can vary because of the shape of the container. So particles in a solid are really close together. And then we often say that they're form a lattice structure because of the very uniform and regular arrangement of those particles in a solid state of matter. Where a liquid, remember we talked about earlier that they roll and slide over each other. So they're going to have an irregular arrangement because they're rolling and sliding around each other. And these particles are actually moving faster, and that's why they're able to roll and slide over each other. Now, in a gas, the particles are independent and they're separated from one another. And so these guys can spread out all over the place. And so all of these are really, when you're talking about a solid, liquid, and gas, you're really talking about how fast are these molecules moving. And so if they're moving really, really fast, then they can spread out. They can move around. If they're a liquid, then they're not moving as fast. So they're going to be slower moving, and they're going to be sliding all over each other. Where a solid, there's not a whole lot of motion. And so they're going to be fixed and closely packed together. And so that's what we can see here. As we increase energy, what are we giving the molecules? We're giving them energy for motion. So the more energy it has, the more excited these particles become, and so the more motion they have. And so you can see I have, this diagram shows an increase in energy. So those particles are becoming energized, and so they're moving around more rapidly. And so you can see these little tiny particles inside each one of the containers representing each state of matter. And so let's look at what's happening here. Where it actually has to do with the force of attraction between the molecules. So in a solid state, the forces are really strong, and they're strong enough to keep them in a fixed position, and they're going to vibrate on each other and rotate in their position. Where in the liquid state, these actually have weaker forces to hold them together because there's greater energy in the particle. And so the particles have greater energy and they are stronger than the forces between them. And so they're going to disrupt that lattice structure. And so that's why they're going to be able to slide around each other. I kind of think of the liquid state as, those bouncy houses that have the little balls inside and the balls kind of you slip and roll over. That would be what a liquid would seem like if the little balls would be the particles. And so a gaseous state, these particles have very high energies. And so that energy is higher than the forces that are being holding them together. And so those forces holding them together are negligible. And so these gas particles are able to isolate themselves from one another. And so that's why we don't have these fixed shapes and that they can spread out in the quote unquote container of the classroom, right? They're going to spread out all over. So how do we change these states? So when we're talking about change in state and we're looking at melting, freezing, evaporating, condensation, sublimation, and deposition, all of these really are talking about, and I know that this word's kind of scary, entropy of the system, where actually is another way of thinking of this is the energy within the system. So if I go from a solid to a liquid, I'm increasing my energy, right? But if I'm going from a liquid to a solid, I'm decreasing my energy. And so I have freezing. So when I'm going from one state to another, it's really describing the changes in energy. So evaporation, going from the liquid to the gas, that would be a gain in energy. Where I'm going from a gas to a liquid, I'm losing energy. And then if I go from a gas to a liquid, that would be deposition. And again, this would be a really dramatic loss of energy. With sublimation, you're going from a solid to a gas. This would be like dry ice. And so we have a really big jump in energy. There is, and I know we haven't really talked about plasma, but you can go from gas, and gas can get really excited and be ionized. That's when lightning forms, because lightning is actually, you're seeing that change in state, you're seeing that really big shift in energy, and so it's ionization, so it's a big jump in energy. So what is that fourth state? So plasma, like gas, has no fixed shape or volume. And what happens is the gas actually reaches a plasma state when the atoms become ionized. That's why it's called ionization. And what happens is it deals with losing or gaining electrons. And we'll talk about that a little bit when we get into positive and negative charges and looking at the protons and electrons. But that's what's happening, is the energy is so exciting that they're actually allowed to, you can actually kick off some of those electrons and it becomes plasma. Recombination occurs when the plasma returns to the gaseous state, and lightning is a really quick ionization recombination. That's when it returns to that gaseous state. Neon signs are actually also ionized atoms. So that's why you see that glow. So it's actually plasma in those tubes. So that's what you're seeing in a neon sign. So changes in state or the phase transitions, again, all involve that heat energy that is either being supplied or removed from a substance. So if I add heat, I'm going to increase the movement or the kinetic energy of the molecule, and so temperature increases. When we talk about temperature is actually that measure. It's a measurement of how much energy that substance has. So the higher temperature it is, the more kinetic energy it has, which means the more movement of the atoms and of the molecules. Now, changes in state are a physical property. So you're not getting a new substance when you change state. You're just describing what it looks like, a physical property. And so we're going to be looking at this in the coming weeks. So when we look at physical properties, melting, boiling, and freezing points and states of matter, those are all descriptions of physical properties because we haven't changed the substance. So I want you to think about what would a solid look like, what would a gas look like, and what would a liquid look like? What would those particles look like in each one of those three? Is this what you imagined? Because that's what you should be imagining when you're thinking of a solid, liquid, and gas. So I hope we have a good understanding of matter and the states of matter. We will be continuing on with more physical changes and actually chemical changes in a couple of weeks. If in the coming weeks and days, if you have any questions, please make sure you're reaching out to me. Bye, guys.